The reason we had to compute the trace formula or evolution operator is that it enabled us to compute the spectrum of the evolution operator, and that was essential to make long-time prediction of dynamics. And that came in two shapes. So one shape was called resolvent. The result of that work was that we got here a sum over the whole spectrum of the evolution operator. Now this works on function space, so there is always infinitely many eigenvalues, but we tend to care about the leading ones. And we found the formula that can be expressed for deterministic chaotic dynamics as a sum of all periodic orbits weighted by the length of the orbit and then divided by the thickness of the neighborhood for the orbit. Now, if orbit was repeated, the neighborhood shrunk exponentially for every repeat. So here we get stability computed once on a prime periodic orbit, but then we get a contribution of every repeat of it. So there's an R here. And then there was a general weight. It said that longer orbits contributed less, and repeats then contributed by exponential power here. And we use this whole theory to compute observables. So we had some fake parameter here. And that was resolvent formula. Now this resolvent formula is true for discrete symmetry as well, but it gets simplified. And the reason why it gets simplified is that the trace became a sum of traces. And this propagates into derivation of resolvent formula. And now the spectrum becomes sum of spectra, one for each irreducible space. Sum propagates through, and on a one irreducible space, we get a new resolvent formula. It says that we will be looking at subspectrum within the subspace, because they don't mix, they're irreducible subspaces. And the formula just looks the same, except it's totally different. So I'm here still summing over alpha equals 0 to infinity. But now this is within one of those subspaces. Now in this sum, if I have degeneracy, if I have an invariant subspace which is of some dimension, that eigenvalue will contribute the number of time or dimension of that subspace. So there'll be a number like this. And now the sum on the right-hand side of the periodic orbits is now the sum over relative periodic orbits. These are the orbits that close in the fundamental domain. They don't necessarily close in the big space. So there's a tilde here. Then the period is being replaced by the period of relative periodic orbit. And now there's an extra weight which came from this decomposition. It says that I have to look at this H, which is where the unfolded full state space version of periodic orbit has ended after one of these short periods of periodic orbits. That's given by this group element. It depends on which periodic orbit, relative periodic orbit I'm working with. So it has a tilde, p tilde thing. And then I have this sum over the repeats. I still have the sum over the repeats. So that shows up here because for every repeat, I get the group operation multiplied. And then I get my weight. But now the determinant is computed. This is now state space, d-dimensional thing. This is group space, so it's order of the group kind of stuff. This is in a full space. And now it has to be computed on a relative periodic orbit, one that's shorter than the original orbit in a full space. Again, raised to the power r. And the weights look like before, but everybody is computed just on a relative periodic orbit. So this is now observable, computed just on one traversal relative periodic orbit, and this is my period of the relative periodic orbit. Important detail is the definition of Jacobian here, which we did, but you were surely forgotten. So the Jacobian of relative periodic orbit looks like what we remember of Jacobians in general. I go time of the relative periodic orbit. So that means in fundamental domain I've returned, and I vary the initial neighborhood. Fundamental domain coordinates. But that means that there is a group element, which is the action of the group on the state space, which depends on this group element, on where the trajectory ended up in a full state space. So this is the correct Jacobian to use. It's totally crucial that you return back to fundamental domain. And for that Jacobian, you can prove that its eigenvalues are invariant and the coordinate transformation. If you didn't have this group rotation back into fundamental domain, this would be just a segment of general trajectory and not a monodromy matrix. It's Jacobian. In this calculation, we have removed time direction. So that's the same kind of monodromy matrix as here. It transfers to the flow. Now this actually also will carry out for continuous groups. This will be a representation of transformation of coordinates for continuous groups, and it will have one dimension less monodromy matrix for every continuous parameter. Structure of the answer is the same.
You will not be able to stay home, brother. You will not be able to plug in, turn on, and cop out. You will not be able to lose yourself on Skag and skip out for beer during commercials because the revolution will not be televised.